Alright, so picking it up again here, here's an example. Let's consider quadratic possibly degenerate polynomials in X. So I sometimes call that P2R, right? So I'm thinking of that as being my vector space, alright? So in that vector space we can either take our usual basis 1x, x squared, or we could look at the perhaps less usual basis, 1, x minus 1, x minus 1 squared. And what I want to do is just look at this vector, a plus bx plus cx squared for arbitrary abc, and I want to calculate the coordinate vector with respect to the beta basis and the beta bar basis and see if we can see how they're related and see how that formula we just derived works out. So to start with, by definition of coordinate vector, you can already see that v beta is equal to abc, right? Now, if we say v is equal to f of x, right, then we're looking to find a bar plus b bar times x minus 1 plus c bar times x minus 1 squared in this context, right? So since we know calculus, we can kind of make our life a little bit easier. Think about Taylor's theorem in this particular case. And so here's kind of, this is kind of a trick for this particular example, but anyway, so like f of 1, well, f of 1 would just be a bar, right? But f of 1 would also be a plus b plus c. And let's see here, f prime of 1 would be b bar, but it would also be, differentiating that, we get b, plug it in 1, right? So b plus 2c. And then, of course, if we take two derivatives and plug in 1, that would give us actually 2c bar. And on the other hand, of course, taking two derivatives, we're just left with 2c, and that's equal to 2c. So that shows us the relation between a bar and b bar. In particular, we've just found that the coordinate vector of v with respect to the bar basis, which of course is a bar, b bar, c bar, right? Well, what are those equal to? Well, they're equal to a plus b plus c, comma, b plus 2c, and, well, this, of course, gives me that c bar is equal to c, right? And so c. Now, if I rewrite that, I can rewrite that as the matrix 1, 1, 1, 0, 1, 2, and 0, 0, 1. That times ABC gives me, you know, a bar, b bar, c bar. And of course, on the left, we have the coordinate vector of v with respect to the beta bar basis. And over here we have the change of basis matrix, p beta, beta bar, and this of course is the coordinate vector of v with respect to beta basis. So that's one way you can just try to, through some direct calculation, relate the expression of the vector in terms of one basis and the other and see what the relation is between the arbitrary. If you pick an arbitrary vector, you relate the coefficients of that given arbitrary vector as they relate to the new coefficients, the new basis, and so that's what I did here. Now the other way, of course, you can go is just to go directly from the definition, which was that p of beta, beta bar, that matrix was the standard matrix of phi beta bar composed with phi beta inverse, right? And so we're looking in a three-dimensional space, so what is that? Well, that's phi, so you feed this, to get the first column, we feed that. We feed it phi beta inverse of E1, sorry about the crying. And then to get the second column, we feed it E2, right? And to get the third column, we feed it E3. But then this is where understanding how the coordinate map works pays off. The inverse image under phi beta of E1 is the first vector in the basis beta, which is 1. So you see what I'm looking at here is just the beta bar coordinates of 1. I need then the beta bar coordinates of what? Well, E2, inverse image of E2 under the beta map gives me x. So I'm looking for and this is the beta bar coordinates of x. And then, of course, the beta bar coordinates of, well, x squared, right? So then the question is, what's the coordinate? So how do you get, then the question reduces to how do you write 1x and x squared in terms of the beta bar coordinates, right? So obviously, let's see here, do it up here. So we have, of course, 1 is equal to 1 times 0 times x minus 1 plus 0 times x minus 1 squared, right? So that puts 1, 0, 0 for the first column. And then to get x, well, x is equal to 1 plus 1 times x minus 1 plus 0 times x minus 1 squared. So that's why I have 1, 1, 0 for the coordinate vector of the second thing. And then finally x squared, just takes a little imagination. That's really x minus 1 plus 1 quantity squared, right? Add 0. And so a little bit of algebra here. That's x minus 1 squared plus twice x minus 1 plus 1, but they're in the wrong order. So I got 1 copy of 1, 2 copies of x minus 1, 1 copy x minus 1 squared. And that's why we had this as the change of basis matrix up there, just the same. So there's an abstract change of basis example. There's another one in the notes that you can look at. Now, let's turn the page here. So what about column vectors? Coordinate change for column vectors. Well, coordinate change on Fn is easier. See, because if we have x is equal to, say, C1 V1 plus dot 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 plus Cn Vn, and it's also equal to C bar 1 V bar 1 dot 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 plus C bar n V bar n, then on Fn we can rewrite this as the matrix C1